So, hello, welcome to you all. So, now we'll start the foundation course on the subject of fluid mechanics. So, my dear, let me know, is there audio and video, everything is clear? First, one thing, 1 second. Audio and video clear? Okay. So, okay. Thank you, everyone. Now, so what is the use, what is the motivation of this course? See, in this course, we are not going to talk very deep. Only we have to touch the basic concepts. So, what is the importance and what you have to get the importance and what you have to get for this series? You have to get this series for that. See, if you start the subject of fluid mechanics, if you start by self or by any reference. So, once you have to start the subject, you just have a knowledge about the fluid mechanics subject. Okay, you must have a knowledge about the fluid mechanics subject. So, with respect to that one, will be discuss the things regarding the fluid mechanics. So, in this fluid mechanics, we have to taking a domain of 4 parts. First one is the introductory part. In that introductory part, we have to discuss about that what is the property of the fluid, and the main property of the fluid. Why? Because if you define the fluid, that property is there must be have a have to understand what is that viscosity, and due to that viscosity there is a viscous shear stresses. So my first topic is today's viscous shear stress. This topic we will cover by 2 parts, part 1 and part 2. Then we will cover the fluid static part. In that part we have to cover with the flow visualization. So in that one we have to cover the flow visualization, all the paths, strict line, path line, all the thing, flow pattern. The last part is the dynamic part. In that one we will discuss the flow through a pipe. That means in generally we have to design a pipe through a viscous fluid. So we must have to know about the properties of all that, where it is losses, what is that, all the things. Then we have to discuss in that one the boundary layer growth, that means flow through an internal pipe. Okay. So my dear, we will start the chapter. The first part is viscous stresses. Now my dear, there are terms that is, if you study the, why you are study the fluid mechanics, that is a very important thing. See, if you are going to any plant, so in that plant there is a very large pipe networking is there. There is a very high pipe. See, this is your one large pipe is there. There is another pipes. These all are pipe connector. These all are pipe is connecting. Now, if you design this pipe, all this pipe connector, that means fluid mechanics play an important role in the design and analysis of the pressure vessel. This is your pressure vessels, like here it is a pressure vessels. So if you design the pressure vessels, piping system, pumps in this one, if you want to fluid the flow, there is a pumping system, pump used in a chemical processing plant or any plant. In that one you must have a knowledge about the fluid mechanics. My dear, if you design, why? Because there is a fluid flow. So fluid flow due to the 3 mechanism. Just remember this thing. The fluid is flowing due to the 3 mechanism. One is due to the displacement of a boundary of the fluid. That means fluid displaced with the boundary. That means when the fluid is contact, that contact boundary will be moved, so the fluid will move. Fluid will move. Second, fluid will move either due to the pressure difference. If there is a high pressure and if there is a low pressure zone, the fluid will move. Number third, fluid will move by the gravity effect. So these 3 mechanisms, the fluid will flow. And when the fluid is flowing, there must be a losses. There must be a losses. Why? Because we are discussing with the real fluid. So there must be a losses. So to account for that losses, we have, why we have to account that losses? Why? Because we have to design the length of the pipe, diameter of the pipe, pumping system is there, all the things in which we have to require the fluid mechanics concept. My dear, in the fluid mechanics concept, one of the best concept, before entering into the fluid mechanics concept, the fluid mechanics generally have a 3 domain. First one is hydrostatic part, second one is kinematics part, third one is dynamics part. My dear, in the hydrostatic part, the fluid at rest or fluid will move as a rigid body. That is your hydrostatic. That means in this one, fluid rest or fluid will move like a rigid body. That means the fluid will move like a rigid body motion. That is the domain of fluid static. That means study of fluid at rest or flow with a constant velocity. That means if there is a flow is a constant velocity, the acceleration is 0. So acceleration is 0, constant velocity, that means the fluid have a no acceleration. In that case, we have to study the hydrostatic. And what are the content part in the hydrostatic? In generally, the most important part of the hydrostatic, you have to find the force exerted by the fluid. Force exerted by the fluid. That means the hydrostatic force. So where the origin of this hydrostatic force? The origin of the hydrostatic force is due to the pressure difference. That means in this chapter, basically we have to study the pressure field within the fluid when the fluid at rest. When the fluid at rest or moving like a rigid body. Now in the domain of kinematics, we have to study the geometry of the fluid motion. That means the fluid motion, that's the flow pattern. Why this topic? And this topic is very important, kinematics part. Why? Because if you visualize the flow pattern, so that you have to design. Let's suppose there is a car is there. Let's suppose this is your car. Let's suppose this is your car is there. Okay, this is your car moving with this one. And there is a fluid is flowing to this pattern. The fluid is flowing. In downside also, the fluid is flowing like that. So this fluid is circulating in this part. So to design the proper effect of this fluid, why? Because if this is your wake region, so if you know the fluid flow pattern, you can easily design the solid part of that system. That means if you design the part of this motion part, must be have a knowledge about the fluid flow visualization. And this fluid flow visualization we will discuss in the kinematics part. Okay. Now, now my dear, the third one is the dynamic, fluid dynamic. That means study of the force that cause the acceleration motion. See my dear, one thing is very important. What is the dynamics? That means force is equal to mass into acceleration. And this acceleration, it is a kinematic part. So if you understand the kinematics part, you can easily find the dynamic part. So first kinematic is there. So we have studied the kinematics. There is that means a motion, that means velocity and acceleration. Basically we have to study the velocity and acceleration. Due to that velocity and acceleration, we have to easily find the force of the system. That means a dynamic part. So in this one, we disregard the cause of the acceleration, the cause of the motion. But in this one, we have to include the cause of the motion. That means a force. So static, kinematic, and dynamic. These are the three areas of the fluid mechanics. But before that, there is a one introduction topic. In that one, we have to study the fluid property. That means the fluid definition with the property. And that property, the viscosity, is very important role. What is that, Vita? We'll see this one. See, definition of fluid. If you define the fluid, how to define the fluid? See, my dear, liquid and gases. Generally, liquid and gases are classified as a fluid because they are substance that continuous deformation. You know this thing. There is not only deformation, these have a continuous deformation. That means it have a no exact any deformation. If you apply the force, there is a certain deformation. No, it will be continuous deformation. That is, this line is the demarcation of the substance of the solid which is differ from the substance of the fluid which is differ from the solid, or flow when subjected to a shear or tangential force. That means the fluid flow required a shear or a tangential flow. How to model this one? How to model this statement? If someone asks you, verify this statement. See, we are taking a sandwich of the fluid, in which one the lower part is fixed and upper part is moving. Upper, there is two plate is there. There is a two plate conductors, in which lower it is fixed and upper is moving. Motion with a constant velocity, you can assume like that. So these are the fluid expanses. These are the fluid expanses. If you take any element of the fluid, so these are the motion, these are the velocity, u. So if you take any fluid element at any point, this point, this point, this point, this point, this point, the fluid experience a resistance. The fluid experience a resistance. Why? We'll discuss. The resistance is what? Resistance is a kind of force. That force per unit area is your stress. That means of viscous stress. Who is the responsible fellow to create that resistance? We will discuss. What is that, beta? What is the model is that? A plate moves over a top surface of the fluid. The deformation of the fluid will continue as long as the shear force is applied. That means if you apply the shear force, if you apply the tangential force, fluid will continuously move. If you apply the shear force. Now, and once it removes, that means if you remove this shear force, it is not like that fluid will come back. That means the fluid will keep its new shape rather than returning to the original one. That is the another difference between the fluid and solid. That means if you apply the shear force, what is the magnitude of the shear force or tangential force? Fluid try to deform continuously. Once it will deform continuously, once you have to remove this load, if you zero this load, fluid will never come back. It will continue deformation. That means once it remove, that means this load, once it is zero, fluid will keep its new shape. That shape will keep rather than it returns to the original position. That means if you are taking any fluid element, let's suppose this is your fluid element initially when there is a no shear force is applied. Now, if we apply the shear force on the fluid, we'll discuss the direction also. That is the very important thing. Fluid continues try to deform to the new position. Fluid continues to try to deform to the new position. Now, my dear, the moral of the story is what? Once you have to remove this load, once you have removed this shear stress, fluid will never come back to this shape. But solid may be within the elastic region. That means if you deform the solid within the elastic region, now if you remove the load, okay, now if you remove the load, solid may be again its shape, but fluid can never. That's why the fluid is called zero memory. Yes, very good question. Saurabh, very good question. Fluid always deform by the external force. That is, what is the minimum force? That is no limit. See, your question is, if you define that question, if there is a solid and if there is a fluid, solid deformation have a certain force required, tangential force. But in the case of fluid, also the force will required, tangential force will required, but that tangential force is not depends upon the magnitude. Whatever the tangential force, fluid is tried to deform. So your answer is fluid deformed by itself? No. And external force is required always? Yes. Okay. So always external force required, no need. So if there is a tangential force 0, there is no any deformation, you can say like that. Okay. Continuous deformation, if you want that fluid have a continuous deformation. So if you want to continuous deformation, you must have always the threshold value of this shear stress is shear force. I hope your doubt is clear. Now, see this line, all fluid element deform when subjected to shear. When subjected to shear. If there is a no shear, no deformation. That's why if you plot the figure graph between shear stress and deformation, if the deformation is 0, if the shear stress is 0, deformation is 0. So, whose fluid which is passing from the origin, that is the actual fluid. Newtonian fluid, diluent fluid, pseudo fluid, all are passing through the origin. That means if the stress 0, deformation 0, from that point the fluid all defined. It is not defined that sir, if there is a deformation, no shear, that fluid actually not defined. So the definition according to that, if there is a shear stress 0, the deformation 0, you cannot define the fluid. It is like that. Basically it is like that. If there is no any shear stress, deformation is 0. That's it. Okay. So if there is a shear stress, there must be a deformation, and that deformation is not a certain value, it is a continuous. That's the define the fluid. Okay. So it is a continuous deformation. See, it is a continuous deformation. And what is this? What is this? This is your shear stress. This is your stress distribution. Okay. Now, so these are the fundamental definition of the fluid. Now next is viscosity. So if you know that, sir, the fluid, if you know that, sir, the fluid is a such kind of a substance that have a continuous deformation. So if there is a continuous deformation, so what they next generate? What if there is a continuous deformation? So what you have to analyze from that continuous deformation? See, my dear, same example. Let's suppose there is a base plate and this is your fixed one. This is your fixed plate. Now this flex and this top plate, it is a moving with a velocity v, and this velocity is a constant velocity. Let's suppose constant velocity, a uniform velocity, let's suppose. So each fluid element is deformed. See this one. Why? Because there must be force, and this force is equal to stress into area. So there must be a stresses there. We'll discuss this thing. So all the points, if you select the chunk of the fluid, element of the fluid, they try to deform. In this case, you never draw the fluid like that. This is wrong. You have always draw the fluid like in a deformed position. In a deformed position. So it will be deformed. Now, my dear, once it is a deform, you know that the fluid will try to deform. So viscosity is a property, so we have to define one property, that is the fluid property. That means viscosity is a property of the fluid that measure the resistance to the movement. That means with the help of viscosity properties, we can find the resistance, and this is the force. That means we have to find the force, the resistance to the movement. Resistance to the movement, that means something is moving, and due to the fluid property, there must be resistance to the flow. And that resistance, why the resistance calculation is important? Why? Because if you know the resistance, that means resistance to, and that resistance will be adverse effect of the motion. So what the power loss, what is the power loss during that resistance of that force, you can easily calculate, so that you can design the component against the viscous resistance. That means if you know the fluid property, you know the resistance to the movement in a very thin layer of the fluid. That means there is a layer by layer. This is the fluid and this is layer. Let's suppose we have to taking this one. We are taking this fluid. See, my dear, we are taking, one second. Let's suppose we are taking this layer. Another one, we are taking this layer. another one we are taking this layer. So it will observe like that, ki sir, we have to create a different layer of the fluid. Why? Because it is a deformation. So if you want a deformation, when the deformation word is satisfied, when we have a look at the fluid have a different layer. See my dear, this layer will be variation. That means you have to taking the layer in a vertical direction. You are taking all the layer in a vertical direction. That means the deformation of the fluid we will measure in the vertical direction. Number first. Number second, that means resistance to the movement of a very thin layer of the fluid over an adjacent one. That means each and every layers have a resistance. This resistance occurs only when the tangential and shear force applied. This is the beauty of this line. That means this resistance, when this resistance is possible, when there is a shear force is there. If there is a no shear force, there is a no resistance. If there is a no resistance, viscosity are not coming into picture. See my dear, if someone says that, what is the viscosity of this fluid which is inside this bottle? You cannot define. See, this fluid are not moving. This fluid is not moving. That means you cannot define the viscosity. So viscosity come into picture when there is a deformation. And when the deformation will induce, there must be a resistance. When the resistance will introduce, there must be a defined viscosity. So these are the line. That means when the shear stress is zero, you cannot define the resistance. That means this resistance occurs only when the tangential and the shear force to the fluid. This is very important line. To the fluid. Okay. Now, how to quantify this one? If you quantify, you have to assume a different thin layer. Why? Because the fluid is continuous deform. That means viscosity is a very important property of the fluid mechanics because it causes the internal frictional within the fluid. That means the viscosity is an internal mechanism due to the fluid itself. Fluid will create a resistance by the another fluid. That means layer of the fluid will create a resistance to the another layer of the fluid. So it is an internal resistance. So viscosity is not a resistance. Viscosity is the coefficient of viscosity is the measurement of the resistance. So see my dear, if you apply the shear force, of the fluid try to deform. Once it will try to deform, that means it will deform, there must be a resistance. And that resistance will be defined the property of viscosity. So viscosity is not a resistance. Viscosity is the fluid property. It will present or not present when there is a shear stress is there or not. Due to the viscosity, we can measure the resistance. Higher is the viscosity, higher is the resistance. But the viscosity is not equal to resistance. Resistance is a force. Viscosity is not a force. So resistance is differ. Yes, but both are proportional. If higher is the viscosity, higher is the resistance. Lower is the viscosity, lower is the resistance. You are here and you are moving into fluid. In the air and in the water. You are moving in the air, resistance is less. You are moving in the water, resistance is high. Why? Why? Because air viscosity is very low than the water viscosity. So the movement of your body is very difficult in the water as compared to air. So in the air, our resistance is less as compared to in the water. So viscosity will measure the resistance, but viscosity is not equal to resistance. Resistance is a force. And force you have to calculate from the shear stress. Okay, so which is produced, so friction which is produced, so this if there is an internal resistance, so this internal resistance, due to this internal resistance, energy must be lost, and to be taken into account, and this energy loss have to taken into account when we design the vehicle, pipes, any channel. That's why this is important. Why the viscosity is important? That is your answer. Why? Because beta, due to the viscosity, there must be an internal resistance, there must be internal friction, and due to that internal friction, produce a energy loss. That means what is the energy will there? That energy will loss due to the frictional resistance, and that energy loss we have to account while you have to design any channel, pipes or vehicles. Why? Because vehicles are moving, so there must be a drag, frictional drag is there. So that is also kind of a viscosity internal resistance. So if you design, you must have a knowledge about the viscosity. Clear? Now, the next one is physical cause of the viscosity. Physical meaning of physical interpretation of the viscosity. This viscosity is your dynamic viscosity. Okay, beta. So viscosity have two measurement. One in the form of kinematic, other is the form of dynamic. So this is the dynamic one. Okay. See, there are two layers. If you're taking two layers, so these are the fixed. So due to the fixed plate, the fluid which is very nearer to the fixed plate will try to move slow. See, this try to move slow, and the fluid which is far from this solid surface, fixed surface, the fluid will try to move faster. Fluid will try to move faster. So there must be a relative velocity. Now that means if you take this two layer, let's suppose if you take this two layer, my dear, if you take this two layer, my dear. One second. If you take this two layer, one second, my dear. If you take this two layer, okay, this two layer. This is layer number one. This is layer number one. This is layer number one, my dear. This is layer number one, and this is layer number two. So this layer number two, which is separated by this distance, this layer number two, which is nearer to the solid surface, and this layer number one is nearer to the moving surface. So there must be this upper layer have a faster and lower layer have a slower. That means this is your faster layer, this is your upper layer, and this is your two layer. So this two layer, layer number one, and this is layer number two. This is your faster layer and this is your slower layer. Both are moving. Now, my dear, what happened? What happened? See, the resistance that gives rise to the viscosity in a fluid, how can be understood? This is my question. The question is that, yes, sir, we understand the resistance that gives rise to the viscosity in the fluid. How can we understood? That means, how can we understood that due to the resistance there must be viscosity? See, this is a fast moving layer, this is a slow moving layer. This layer composed of molecules, and this layer of the composed of the same molecules, let's suppose. Now, my dear, think these molecules. If you think this molecule, my dear, if you think this molecules A, if you think this molecules A, if you think this molecules A, okay, and if you think this molecules B, so this molecules B, and this is your interface. This is your interface. This is one layer, this is another layer, and this is called, this is your interface. That means this is your interface. This is your interface. This is your interface. Once again, this is your interface. Okay, this is your interface. Okay, so this is your interface. One is the fast molecules movement and other is the slow molecule movement. What happened? See, what happened? When the molecules A, this is the molecules A, in the faster top layer happens to travel down to the bottom layer. That means this fast layer will be try to move down to the slow layer. Why? Because these molecules try to slow down these molecules. Yes or not? These are the relative motion. So these molecules have a slow motion, this molecule have a fast motion. So what we have to do, what the molecule, slow molecule want that this slow molecule want to slow down. That means the molecules B will slow down the molecules A. Molecules B will slow down the molecules A. That means slow down the bottom layer to the slow down bottom layer. It will have a component of the motion in the right direction. That means, see, so if we slow down, these molecules have this direction component, yes or not? This direction component. This is the direction of a component, velocity. Now, this is your resultant velocity. It's have a two direction. First, it is in this direction, and second one, it is in this direction. That means this will be try to maintain the momentum, maintain that, and this will try to diffusion. So these are the diffusion. These are the diffusion. Okay. So it will have a component of the motion to the right. So these are the motion. This is your motion in the right direction. Now, collision that occurs with any slow moving molecules to the bottom layer will cause to be pushed along due to the momentum exchange with A. That means this velocity will try to impact on these molecules, impact by this vertical velocity will try to impact these slow molecules, and these slow molecules try to eject in this direction of the faster molecules. So these molecules again have a two component. One is the vertical component, other one is the horizontal component. Now, my dear, this horizontal component is slow, this horizontal component is fast, so there must be a relative motion. And this component is a try to momentum exchange. So these are not a momentum exchange, these are the momentum exchange. That means the diffusion of the momentum. So this velocity component, vertical velocity component, is try to diffuse the momentum, and this horizontal component of the momentum, this horizontal component of the velocity is a try to maintain the momentum. Okay, so the layer will be caused into the push along due to the momentum exchange with A. So there must be a momentum exchange. Now, the reverse effect occurs when the molecules B in the bottom layer migrate up. So it will also exchange the momentum. This A will try to enter into the slower molecule, it exchanges the momentum. Same, it will try to enter into the faster molecule, it will exchange the momentum. So there must be a momentum exchange. Now, here this slower moving molecules will retard the faster. Slower moving molecule, here the slower moving molecule will retard the faster molecules, moving molecules through their momentum exchange. Both of this effect can rise of, both of this effect can cause the resistance or viscosity. And there must be this is a resultant component. So this component and this is a resultant component. So there must be a diffusion. So in this direction, there is a diffusion of a momentum. In this direction, there is a diffusion of a momentum. Diffusion of momentum. Now, my dear, higher is the higher diffusion of the momentum. Higher is the higher diffusion of the momentum. Let's suppose the diffusion is high. Then what happen? Higher is the higher diffusion of momentum. That means higher is the higher viscosity. Higher is the higher boundary layer growth. So higher is the diffusion, higher is the viscosity. Lower is the diffusion, lower is the viscosity. Clear? Now, if the diffusion is high, the relative motion is low. Yes or not? See, in this is your, see, this is your resultant component. So this is direction of diffusion and this is the direction of motion. So if the diffusion is higher and higher component, so this is your lower, so lower. So this is lower, that means this causes the motion. So motion, higher is the diffusion, lower is the motion, and lower is the motion, higher is the viscosity. Higher is the viscosity, higher is the diffusion. Clear? That means in this direction there is a diffusion, and how much the diffusion will penetrated up to that, that will be a messenger effect, and that will measure the resistance. Higher is the higher resistance, lower is the lower momentum. Maintain the momentum. So in this direction, diffusion of a momentum, in this direction, maintain of the momentum. And that two are relative parameter will measure by the kinematic viscosity, so that kinematic viscosity is your dynamic viscosity density. Density is the measurement of momentum, inertia, and this is diffusion momentum. So how much the momentum will diffuse to maintain the momentum, that is your kinematic viscosity. That is your kinematic viscosity. This is a physical interpretation. Clear? Now, the next one is, so I hope it is clear. If there is any confusion, you can freely to ask anything in the fluid mechanics. It's my challenge. Okay? Now, if you understand the viscosity property, how to understand the viscous stresses? How to understand the viscous stresses? See, my dear, if you understand the viscous stresses, see, if there is a motion of the fluid, there must be a deformation. If there is a deformation, there must be a resistance. If there is a resistance, there must be a diffusion. If there is a diffusion, there must be a viscosity. That is clear. So higher is the higher diffusion, propagation, higher is the higher diffusion, propagation, higher is the higher boundary layer growth. Higher is the higher boundary layer growth, higher is the higher region of the viscous. So within the boundary layer there is a viscous region. That's why. Clear? So how to define the viscous stresses? Let's suppose there is a same fixed plate, there is a same moving plate. The moving plate is moving with a constant velocity v. This is a fixed plate, so this is your fixed plate. Fixed plate. This is your fixed plate. Now, my dear, let's suppose this is our element, fluid element is there. Now, if you apply this force, this element is trying to deform, so it is all the fluid, all the location at any point, the fluid is in a deformed position. Let's suppose you have to take one chunk of the fluid. Let's suppose you have to take one chunk of the fluid. Let's suppose this is your element. So this element, it is not a deformed shape. So this is axis. If you measure, let's suppose you have to measure, this is your y-axis from the fixed plate. So my dear, one thing is very important, that this y coordinate is a fixed coordinate. This y will measure from the fixed surface to the fluid 90 degree from the surface. That is always fixed. What is the fixed value? What is the y fixed? Y is always from the fixed surface to the fluid at a 90 degree of the fixed surface. So that is fixed. So these are the y component. If you take this fluid element like that at this position, why? Because this is not any movement. This is the element of the fluid. Now you have to apply the stresses. This fluid element is trying to deform like that. This fluid element will try to deform like that. So this fluid element have a high velocity as compared to this fluid element. Why? Because this will retard and this will accelerate. Why? Because this fluid upper part will be nearer to the high velocity field, and this lower part is the nearer to the low velocity field. So it will try to deform. Now if you take, that's why if there is a velocity, this, see how it will distribute it. See my dear, this is your y-axis. Now if you are taking this fluid element, this is our fluid element. So at the lower portion, at this one, this is a very important notation I am telling you. at the lower portion of this fluid element have a velocity, let's suppose u. Why? Because it is not at the bottom of the plate. Why? Because at the bottom of the plate, due to the no slip condition, this velocity is 0. But it is little bit far from the plate, so this edge is near to the solid surface, so this velocity is u. But this edge of the top fiber of the fluid will be higher velocity, which is u plus delta u. So that's why the velocity is varying, and the variation of the velocity along y-axis. The variation of the velocity along y-axis, and which component of the velocity? X component of the velocity. So how to denote this one? Velocity in x component denoted by u. Yeah, you can say that ux. So ux is the velocity in x component, and that will vary along y-axis, y direction. Why? Because the deformation, the layer, it is, you have to take a layer by layer. It is in a y direction. It is in a y direction. It is in a y direction. So it is a function of y. So all the layer, let's y equal to 0, the fluid is rest. Y is equal to h. Let's suppose the gap is this. Fluid is have a higher velocity. That is u, plate velocity. So velocity distribution within this thin fluid layer. This is a thin, very thin. Thicker, they have a different velocity profile. So what is, how to quantify this one? Let's suppose this is our fluid element. Let's suppose, my dear, this is our fluid element. This is our, one second, yes, it is like that, one second, okay, this is our fluid element. Let's suppose initially, okay, one thing, this is our fluid element, this is our fluid element. Let's suppose this is our fluid element, clear na? This fluid element, thank you Pratik. This fluid element have a top one, have a velocity which is higher velocity. Let's suppose this velocity is u plus delta u. Let's suppose this velocity is u plus delta u, and this lower velocity is u. Now, my dear, why we are designing this one? Now, due to that one, let's suppose this is your A, B, C, D. So due to the high velocity, this A point, this is the points, let's suppose, and this is this point. Let's suppose we have to measuring reference line this one. Now this high velocity, this A point, after some time it will move at this point A dash due to this velocity during t time. So what is the displacement? The displacement is velocity. Displacement is u into delta u into delta t. This is the displacement. Now this is your low displacement. Why? Because low velocity. So it will displace at this point d dash. So now if you join this new position, it is look like that. So these are the velocity profile. Now, my dear, my question is why this is important? Why this profile is important? The question is that why this is important? Why this is important? Please tell me. Why we are thinking in this direction? Please tell me, my dear. This is very good question. Why? See, why this is important? Why? Because if you define the new position of the fluid, what is the new position? Why? Because it will continuous deformation. If the fluid is continuous deforming, so what is the new position of that fluid element after delta t time? There must be have this pattern. There must be follow this concept. That means if you define, that means why this is important? Why? Because if you sketch new location, why this is important? If you look at new location of AD, which is like this is important, which is like this. For that one, this sketch is important. Okay. Now, my dear, think that one. So, what we realize that, see from this diagram, what we realize that has a not only got displaced linearly, but it has undergone an angular deformation. See, my dear, this is very important information. These are the birth of new concept. What is that? If you try to think like that, the fluid element not deform linearly only, it also deform angularly. So there also be angular deformation. It is not like only linear deformation will take place. If you apply the force, the fluid will deform. It is not deformed only linearly, but also angular deformation. And that angular deformation is called shear deformation. Okay. So this is your angular. See, this is the angular deformation, yes or not? See this one. If you try to draw the line, from here, if you measure this, try to draw the line. Let's suppose this is y direction. If you try to draw this line, so this is not only linear deformation, also there is an angular deformation theta. And this angular deformation is known as shear deformation. This is known as shear deformation. No problem. It is like a linear you can take. I am not in a scale manner. You can take a linear also. Okay. You can take, Pratik, you can take beta linear also. It is not like a parabolic. You don't think this is a parabolic. It is a linear. You can think like that. Okay. But if there is a linear, also there is an angle. See, there is an angle. So this fluid element not is only linear deformation, it also the angular deformation. Clear? This is clear? Not so? That is clear, beta? Pratik? This is clear? It is not like a parabolic. You can think like that it is straight, no problem. Okay? If you take a very near point, near, it must be a straight line. So it will be a straight line, no problem. You think both in direction, either parabolic, either linear, no problem at all. If there is a very small thin gap, there must be a linear. That is good. Okay, so that is the birth of shear deformation. Someone ask you how to justify that fluid have a shear deformation. So you cannot say that, sir, if you apply the tangential force, there must be a shear stress, so there must be a shear deformation. No, shear deformation, the birth of a shear deformation is due to the angular deformation, not linear deformation. So how the angular deformation will quantify? The angular deformation will quantify when you have take the fluid element after delta t have a new position. So that you have to define the angular deformation. According to that angular deformation, you can define the shear deformation. So shear deformation is a kind of angular deformation. Clear? Clear, beta? Clear, everyone? Okay. Now the next question is that, how this shear deformation quantify? That is the very good question. The next question is that how this shear deformation quantify? That means how this shear deformation can be measured. For that one, this is our arrangement, initial arrangement, velocity distribution within the thin fluid layer. Velocity distribution. So now next question is that you have to understand that there must be a shear deformation. Now the next question is that how to quantify this shear deformation. So my dear, think this one. this is your two fluid, this is your fixed plate, these are the moving plate, this is your y direction. You apply the tangential force, this is your tangential force, yes, shear force, this is your shear force. You apply the shear force, each and every layer is tried to deform. So this is at y position, this is at y location, this one, this one, this one. So this act as shear stress, yes or not? This will act, how to define the direction we'll discuss. So this will act as shear stress. This shear stress, this is very important. This shear stress deformation, this shear stress will cause the shear strain, will cause the shear strain. So let's suppose this layer, this distance is your delta y. This distance is your delta y. Very big. That means distance between this thin two layer, distance between this two layer, thin two layer. The upper layer moving with u plus delta u, lower layer moving with u. So it is like that position, and that are the shear strain. So someone asks you, if you, this is your stress, shear stress. Due to that shear stress, cause of the shear stress is a shear strain. So how to measure the shear strain? You can easily measure. So this is your y distance, and if we measure this point will shift, how much it will shift? At this point, it will shift at a delta x with respect to 0. It will move delta x. So it is not movement only linearly. Just now we have to see that it's have an angular deformation. So let's suppose that angular deformation is delta alpha or delta theta. These are the parametric point. Now, so if we take this one, so what is alpha then? What is 10 delta 10 del alpha? This delta x or del x by delta y. What is a delta x, beta? Delta x is nothing, it is your delta u, that means change in velocity, delta u into delta t. This is your delta x. What is the displacement? Delta u into delta x. Now this is your delta y. Clear? That means this delta u, that means if you take like that, now my dear, this deformation is very small. We have to measure the very small deformation. That means you have to take this tends to be 0. So if tan theta tends to be 0, if tan theta, that means theta tends to be 0, so tan theta is theta, that means this is del alpha. So del alpha is equal to del u del t by del y. So if you take del alpha by del t is equal to del u by del y. No problem at all. No problem at all. Now, so this is your main equation. Now, how to analyze this mathematics? This is the mathematical model. How to analyze that? See, how to analyze that? If see, what is that time? We have to measure very short interval of time. Why? Because the angle is very small. So we have to measure very small angle for a small angle of time. So if there is a small time, so let delta t tends to 0. If delta t tends to 0, and already we know that delta y is 0, that was very adjacent fluid layer, and that adjacent fluid layer, the distance between these two fluid layer is tends to be 0. So put the limit. This is a very important thing I am telling you. That means here you have to put limit delta t tends to 0 del alpha by delta t, very short time, during a short two consecutive layer, that means delta y tends to be 0, not equal to 0, not equal to 0, tends to be 0. So delta u by delta y. Now my dear, if you remove this limit, this is your d alpha by dt is equal to du by dy. These are the quantification. What is this? D alpha is what? Angular deformation. Divided by t, that means this is rate of angular deformation. This is your rate of angular deformation. It is measured written as alpha dot. This rate alpha dot is equal to velocity gradient. These are the slope of the velocity gradient, du over dy. From this one you can measure. Now my dear, you can, why? Because see, practically you cannot measure d alpha by dt. Why? Because if you apply the shear stress, fluid is continuously deforming. So how can you measure d alpha? You cannot measure. So for that one, but this one you can measure. There is a velocity profile. There is a velocity profile. You can just differentiate it. That differentiation, that slope gives directly to your angular strain. Not angular strain, but the rate of angular strain. So my dear, see this one. This is not measuring. You cannot measure this one. But this you can measure. Once you have to measure, that equal to the rate of angular deformation. This is the beauty of this quantification. This is the beauty of this quantification. How to measure the rate of angular deformation. So this you have to measure. So one thing is very important from this slide. Shear stress, you have to produce the shear stress. The cause of the shear stress is the shear strain. And these are if taking a continuous deformation for the fluid mechanics. So this is not a shear strain. This is a rate of shear strain. Yeah, rate of angular deformation, and that rate of angular deformation is your velocity gradient. Clear? Clear? Clear, beta? Now, the next question is that. What is the next question? Next question is that, my dear. Who is the responsible of this shear strain? Who is the responsible of this angular deformation, beta? My next question. Who is the fellow which is responsible to this angular deformation? Yes, shear deformation. Who is the responsible of this angular deformation? The responsible is shear stress. Who is the responsible of this angular strain? Shear stress. So the question is that who is the responsible of this angular deformation? The responsible fellow is your shear stress. That means higher is the higher shear stress, higher is the higher rate of angular strain. Higher is the higher rate of shear stress, higher is the higher angular strain. That means the angular strain is responsible for the shear stress. That means higher is the higher shear stress, higher is the higher angular strain. That means tau shear stress is directly proportional to alpha dot. Clear? 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 That is your angular strain. Now, if you remove this proportionality, you must have to introduce one property known as dynamic viscosity into alpha dot. That means this shear stress is your function of alpha dot. Higher is the higher shear strain, rate of shear strain, higher is the higher shear stress. Now, so in that manner, you can define tau is equal to mu, and this alpha dot is nothing du by dy. That's why, and this is called Newton's law of viscosity. This is called Newton's law of viscosity. This is called Newton's law of viscosity. So we have to successfully prove. Is there any problem up to this one? Please tell me. Now, my dear, if you study that equation, so we have to apply that equation for some engineering application. What is that? Common engineering model. See, you just observe like that. There is a vehicle, and this vehicle are moving in the wet road. That means there is a raining season. In the raining season, the vehicle is moving. Now, you have to apply the brake. You have to apply the brake to stopping the car. The car will skid after a certain distance. So there must be there must be a hydroplaning between the tire and the road. So what is that? I will read this question. See, I will read this model. What is the model? ABS, correct. ABS, correct. What is the model? When a vehicle such as automobile slams on its brakes, locking the wheels. That means we want that lock the wheel. On a very wet road, that means on the road there is a fluid. It can be hydroplane. It can be hydroplane. That means on this one there is a plane of the fluid. In these circumstances, a film of water is created between the tire and the rod due to the hydroplaning. That means there is a rod is there is a tire. In that one, between that, there must be created a thin film of the water. Theoretically, a vehicle could slide a very long way under these conditions, though in the practice the film is destroyed before such distance are achieved. Indeed, the tire treated as a design to be prevent the pre-resistance of the such film. That is, if you take this view, that means this is your road tire, this is your tire, this is the motion of the vehicle. Let's suppose V is the motion of the vehicle after applying the brake. This is after applying the brake, beta. We are talking about the case when the brake is applied. It is not that we are moving the car. No, this velocity when we are applying the brake. Clear? We are applying the brake. So while applying the brake, there still have a velocity. So this, and there must be a road which is fixed. In that one, there must be a fluid. That is called hydroplaning. So this tire will move in this direction with a velocity v. So this tire act as a moving plate and this road act as a fixed plate. In that one, there must be a hydroplaning. Let's suppose this hydroplaning is your h distance. So there must be a, so in this case, this surface is your moving in this direction. So in this case, my dear, in this case, there must be a, what we have to do? We have to think like that. One second. There must be a hydroplaning. That means in this case, motion h. So this is your tire. This is your tire and motion, and this is tire, and this is fixed, and this is your hydroplaning. And this model is called what? Caught flow. This model, we have to model this one as a caught flow. That means flow in between very thin narrow region. That is called caught model. Caught flow. This is a very common model in the engineering practice. This is very common model in the engineering practice while you have to design the races. That means tires are designed to prevent this skid. To prevent this skid, you have to design the tire. So while you have to design the tire, you must be follow the caught flow model. The caught flow model. So my dear, I think today time is end of here, but tomorrow we'll also discuss at 6 to 7. From here continue, okay. Hydroplaning, see, hydroplaning must, see, what is the hydroplaning? Hydroplaning, that means two factors. See, density is the fluid property, viscosity is the fluid property. So hydroplaning will depends upon the density and viscosity also. Yes, there is a water, fixed density. So it is in not depends upon the density. Density is the fixed. Density, it is not like that hydroplaning, the model is hydroplaning what? The model of hydroplaning is based upon the viscosity, not based upon the density. Why? Because density is fixed. The fluid have a density fixed. What is that? There is a water. Raining season, there is a water. Density is fixed. Viscosity is also fixed. Viscosity is also fixed. But it is not that, sir, hydroplaning, this is the hydroplaning, that means this is your h distance is the gap. So this gap, it is not like say that, sir, hydroplane, higher is the higher viscosity, viscosity is high. The fluid, let's suppose there is oil is there. So viscosity is high. So what is the hydroplaning? Hydroplaning is what? High. That means there is a thick fluid. If there is a thick fluid, viscosity is high. So if there is a thick fluid, the h distance is high. If there is thin fluid, h distance is low. Number first. If there is thick fluid, h distance is high. If there is a thin fluid, h distance is low. So according to h high or low, that will depends upon the viscosity. But in generally, we are not disregarding the density. We are regarding only viscosity. So hydroplaning, your answer is hydroplaning depends much more about the viscosity. It is not much more depends upon the density. So your answer is, sir, hydroplaning depends upon the viscosity of the fluid or density of the fluid. Option is viscosity of the fluid. Option is viscosity of the fluid. Okay. So my dear, we'll continue with this session tomorrow at 6 to again 7 p.m. And what is the motive of this session? Again, we have to cover. Again, there is a common engineering model, and also try to solve some boundary condition like based upon the no slip condition. And from the boundary condition, we have to try to solve two very good problems, so that you have to understand the two things. In the tomorrow classes, what you have to understand the what is your free surface, what is the consequence of the free surface, what is the force will exerts on the free surface, number first, and what is the stresses within the fluid if you take a thin lamina. If you take a thin lamina, what is the shear stresses, what is the direction? Why? Because shear stress have a direction also. Shear stress have a tensor quantity of order 2 like x, y. So okay, Pratik. Okay. I don't know, but thank you very much, beta. Such type of appreciation, very good. Such type of appreciation I really like. And if you are very good, it is my very good things. Ki you just inform me like that information. Okay, beta. That is very good thing. I will just share. So I think you are which year student, beta, and where you have to go when you have to get the IIT admission in your, sir, you are which at where you have to contact me, that means at what time I didn't recognize, but no problem. You are my student, and God bless you always, and you always fight from the adverse condition. Okay. Okay, Pratik. Okay. So it's my blesses is that always fight from the adverse condition. Very high motivation. Okay. So we design always in the adverse condition. Favorable condition you can handle. My blesses that in the life, when you have a adverse condition, you just fight it and get the result. Thank you. Bye bye.